Hi, welcome back. I hope you're caffeinated and enthusiastic and kind of ready to go for the next round. So next I'm going to introduce Sam, who's also not quite a colleague, but someone that I run into quite often. Sam is someone who is passionate about technology. He has been a serial contributor to a number of different open source projects, but is also, I would say, a serial contributor to the community, somebody that I see at conferences, who participates really well, who looks out for other people. I'm super excited to have him personally here, but also to have this talk included on the schedule today. We're talking about Git, and Git, it's such a key skill. To understand Git is to be able to participate in software development of all kinds, regardless of which language you write today or learn next year, regardless of what level you're participating in as a developer, whether you work on your own or with a team, Git is your special magic dust. It's a massive enabler. So I'm delighted to introduce Sam to tell you about Git.
Thank you very much, Lorna. Okay, my name's Sam, and my talk's called Git's Guts. I was very excited to do a talk here because this is my first proper conference talk. I've spoken at a few user groups in the past, but this is my first one. Lorna, who's kindly introduced me there, is a published author on Git. That's not making me nervous in the slightest. No, it just means at the last minute I actually had to fact check all this, so I was going to just make stuff up. Okay. Now, what I'd like to talk about is commit storage, branches, merge commits, reflog, rebasing, cherry picking, working with remotes. When I want to talk about Git, I think it's a topic that, for me, a lot of developers know a fair amount about. A lot of people find that they've used it for quite some time, but that it somehow continues to surprise them at the moment when it's the most inconvenient. And my own personal experience with Git was that I started using it and then went through this sort of horrible phase of being the only person on the team who was using up SVN until now, and it kept stealing all my work and refusing to give it back. And every time I would think I was doing the right thing, somebody would come over and advise me in the strongest possible terms that they disagreed. And then I learnt a sort of 4 or 5 commands by rote that seemed to work most of the time, and then kind of stopped learning about it for 3 or 4 years before I started to actively look into how it actually works. And I find that that's often the case with PHP developers. It's often the case that they're familiar with Git to the point of being able to use it successfully most of the time, but haven't really had a chance to look into it in too much detail. So this isn't an introductory talk. It's not a sort of first ever introduction to Git. But I'd just like to look at some of these commands, many of which you may have heard of in the past, and discuss what they're doing in a bit more detail. And perhaps there'll be some surprises along the way. So the first thing we do, as we work through our Git repository, is type git init, and it tells you it's initialized an empty Git repository. So things are going great so far. In fact, it seems to have just worked in a way that's made me already suspicious. But the important thing to note about this is that when it says that it's created this .git directory, that is, as they say, all she wrote. There is no central database, there's no daemon running, there's no secret hidden place somewhere on my laptop where all the important stuff's kept where I can't see. It's all in there. Hasn't done any network communication like anything like that yet. So we've created an empty repository, and everything we need to know about it, everything Git needs to know about it, is in this .git folder, which looks like this. Now, there's a lot of stuff in there that may or may not make sense to you. Some of you have probably heard of Git hooks. You've probably heard of branches, refs. Objects is sort of means commits, but There are some things in there that we are going to look into today in more detail and some stuff that's not as relevant. But moving on to making our first change, we've created a file. I've written the words hello world in it. I've typed Git'S in a file name. You can use -- all or --A if you want. And I've asked Git what the status is. And it's saying changes to be committed and use git rm --cache to unstage. Now, what it's adding to is variously on different man pages called the cache or the index or the staging area. In fact, it's managed to use 2 of those terms in a single sentence, but it's all the same thing. It's very difficult to write a talk about Git without there being this recurring theme of that's not what it's actually doing, it's lying to you, or that's phrased really badly. I don't want to be too critical of the tool, but it's the cache and the staging area and index are kind of one thing. And at the moment, this is still very much a work in progress. So we haven't committed yet in the English language sense of the word. We haven't formalized this. We haven't created an immutable commit object yet. So let's do that now. We type git commit -- message and my first file with an excitable exclamation mark. And what we see in the output is it's saying, yep, I've done it. And it's showing 7-letter random string of nonsense. This is the short hash, so every commit has an ID number, and there'll be a lot more on that later, but this is the short version of that hash, the first 7 characters. Now, armed with this knowledge, with this short hash, we can start to find out more about what gets actually stored. So commit objects are described as immutable here. Git sometimes uses the phrase commit or commit object in the docs. Sometimes you'll come across manuals that use the 2 terms interchangeably, and they're immutable. There's lots of commands like git commit -- amend, which pretends to be amending a commit when it's actually not, it's creating a new one. It's helpful for our purpose to think of the commit as never going to change, even if there are times when it is as if it had, if you see what I mean. We'll cover that in more detail in a moment, but the commit consists of 3 things. There's a change set, payload, the actual commit body, which is me writing the words hello world. There's some metadata about it. It needs to store who created the commit, what the message was, there's timestamps in there, things like that. And the commit has an ID number. We've seen the abbreviated version so far, using which we can now have a look at the log, and we can see in this abbreviated version of git log, which is showing what's going on in the repo, we've used a command line flag there to make it smaller, but it's just showing us that there's 1 commit so far. So it's not a very exciting commit graph, but this is what it's created. This git show followed by the hash, which I've cut and pasted out of the log. Now what we can see here is a bunch of metadata, and at the bottom, the change set, what's been added or subtracted. So this is how you can look at what the commit's actual payload is. There's also a metadata file in there, and you don't necessarily want to have to go rummaging around in the .git directory to find it, so there's helpfully this cat file command to output it for you. Now, this has an author and a committer as 2 different people. There are times when that seems useful. We'll cover cherry picking later when it makes sense to talk about a commit having been created by one person, applied by another. And it's got timestamps, it has the long version of the ID, and the commit message. Now, it just so happens that if you take this file and put some kind of left padding on it that I can't remember, and use the SHA-1 hashing algorithm to hash it, what you get is the ID, which is why git commit -- amend, when used to change a commit message, isn't creating the same commit, it's creating a different one with a different ID, because the message, which is there, is sort of baked into this hash that defines what the ID is, and that's something that's going to become important as we progress, but for the time being, we've had a look at the commit and discovered that it holds the change set, metadata, and it has an ID number. Now, we quickly add a second, even more exciting line of text and commit it again and have a look at the log. We've now got 2 commits with 2 different ID numbers and 2 different messages, and cutting and pasting the terminal output is as close as I dared come to a live coding demo and my first ever talk. And drawing coloured circles was as close as I dared come to turning up with a large whiteboard and a camera and telling Lorna at the last minute that I need an extra camera angle. So we've got coloured circles. They strongly resemble Ryman's fridge magnets because on times when I've done training internally at previous employers, it's all just agile stuff. You use post-it notes, you use coloured fridge magnets that are lying around. So we've drawn a diagram of a very exciting commit graph here. And if we have a look at the metadata for the second commit, it's got one extra thing in it that wasn't there before, which on the third line is that it's got the parent. So the commits know who their parents are. So what that means is, for the time being, our 2 commits are essentially a sort of singly linked list. If we use the git log command with the -- graph flag, it even draws this with an ASCII dotted line for us. So if I update my diagram now, the second commit, being the one on top, has a pointer to the first commit. And that's how the commit graph has been stored. But if we take a careful look at the log command, there's some extra information in there as well that's going to be interesting. Just before we move on, this is obviously, at the moment it's just, I've said it's sort of a singly linked list. It'll start to look more like a tree later. There are always some kind of what you might call a directed acyclic graph, which means blobs and arrows, and the arrows can't go round in a circle. Now, if we type git log -- graph -- decorate, it puts 2 little stickers on the top fridge magnet. That's really exciting. One of them is called master, and the other one's called head. Head is attached to master in the sense that there's an arrow pointing to master, and it's on a particular commit. So that represents what's actually on the file system. If head's on that second commit, that means if I look in the files, as long as there aren't any uncommitted changes, then they'll be up to date. And master is the name of a branch. If we have a look in the .git directory, we can see what the branch is. It's in .git /ref /heads/ and then a file called master with a hash in it. And this hash is the hash of the most recent commit. Now, I was told I had to include at least one meme in my slides. I didn't even have to create this myself. There's like 12 of them on Google Images. So what we've essentially discovered is that the branch is a named pointer to a commit. It's a pointer because it's got the commit hash in the file. It's named because it has a file name. And there's no other interesting metadata in there about who created it, no reason why, no message, no timestamp, none of that. So we've got as far as having a look at how commits are stored, having a look at how branches are stored. We can create another branch whenever we want. This is simultaneously Git's greatest strength and its greatest weakness. It's a bit beyond the scope of this talk for me to rant on about continuous integration at this point, but both the angel on one shoulder and the devil on the other are saying it's very easy to create branches in Git. Make it that way you will. So we've created a new branch called feature, which is on the top commit. It's just another sticker on our fridge magnet. And if we have a look at what's actually in that feature branch, we can check it out and discover that it's the same because the files haven't changed. Head is still on the same commit. It's just we've attached it to a different branch now. So that shows what branch we're committing to. Just as an interesting aside, if we now are shouted at by a project manager who says, why is there a branch that hasn't got a JIRA ticket number in it, which is an experience I've had several times. If we try to create a branch called feature/proj123, we get an error. Normally this would be okay, it's fine to have slashes in the branch name. But remember that the branch was just a file in this Git'S refs heads folder. It's now trying to create a folder called feature where there is a file called feature, and the file system's saying no. So we can learn from that if there's a slash in the branch name, the branches, it actually creates folders for them based on sort of the first half of the branch name and then a file for the second half. So in this case, as a constraint of the file system, it hasn't been able to create it. But to get back to our repository, we can now commit a third commit to the feature branch. Now what's happened is the new commit object, which is at the top in blue, has been created. Head is now on the new commit. That shows what commit we've got checked out. And because head is attached to feature, when the head label moved up one, it dragged the feature label up with it to the top. So this concept of head being attached to a branch just means if you do a commit, this branch pointer is going to move to a commit that's higher up on the diagram. That's all it really means for head to be attached to anything. Now, we've talked about commit storage and how branches are stored. I'd like to talk a little bit about merge commits now. But before I do, just a quick summary. We've seen that Git's storing commits in the file system in the .git folder. We've seen that it's storing a sort of payload or change set or commit body, and that there's metadata for commits and that they have IDs, which are a hash of that metadata. And we've seen how it's storing a branch being a pointer to a specific commit. So now, if we fast forward in time a little, the repository is now ready to have a merge commit created. So all that's happened is master's advanced. Interestingly, if we just did the previous .log command with just the first two flags, we wouldn't actually be able to see the master branch at this point. But we've added --all at the end of the command. So that's making it show us the whole diagram with all of the branches that have been created in the repository, and the ASCII art arrows have to cross over sometimes, and it starts to look a little bit of a mess if you do that, but on the whiteboard it's hopefully nice and clear because the repository is mercifully small. So what we want to achieve now is we want to get this brilliant code that somebody's written and put in the master branch, represented by a pink dot with the word master in next to it. I want to get that into our feature branch. So we're going to do a merge. We type git merge master, and it merges the feature branch. It merges the master branch into feature. So we have a commit, which now has two parents. Still a directed acyclic graph, meaning that the way the arrows are pointing, you can't go around in a circle. But we've advanced the feature label to beyond this new commit, and head's been advanced, and we've now got our merge commit. The second argument on the command given is optional, but so if we have a look at the metadata for this commit, we can see it does indeed have two parents over there. So merge commits, there are different merging strategies. There's all sorts of fun you can have with things called octopus merges, which are exactly as clean and simple as they sound, but our merge commit, has two parents. And it has an automatically generated message. I've just gone with the default one there. There's other things you can do as well. It's possible to put other change sets into merge commits. If we have a look at this merge commit, we see that it does actually have a body. They don't all, but there was a merge conflict. And because there was a conflict, that conflict was resolved. I've resolved it manually. And then the place that that data goes is in the commit body of the merge commit. So in this case, we've had to remove a line that was present in one branch and a line that was present in another branch and come up with a compromise between the two. So This merge commit, it would have been possible to add any number of changes to it, whether they were related to the conflict resolution process or not. I had promised that this talk wasn't going to be sort of advocating a particular workflow, but I'd urge you to reconsider. I'd urge you to reconsider if you're planning to do that. But we did have a merge conflict in this case, so it has got a body. Now, if we want to undo the merge, if we decide that we don't like it, if we decide that the code that we've just pulled in from the master branch is rubbish and the person who wrote it's an idiot and shouldn't have inflicted that on us, we've got a couple of different options. There's a few different ways that you can do that. There's a command called git_revert, which produces a new commit, which undoes a previous one. There's a command called git_reset, but just for fun, we're going to do it in a more manual way here. So what we want to do is have a look at the log output, identify the commits that we wish we were on, which is on the left, second from the top there in blue, where the feature branch used to be. And all we really want to achieve is picking that label feature up and sticking it back on the one underneath. So all we need is to get the commit graph back into a previous state where the feature label is on the blue circle underneath where it currently is. So having looked up the ID of the commit that we want in the log output, we now check out that commit. And we get an alarming message saying we're in a detached head state. Don't panic, everything's fine, everything's under control. It's just, I think, possibly Linus Torvalds as being a bit of a drama queen. It's not as bad as it sounds. So we've succeeded in checking out the commit. So we've now got head on the relevant commit. In fact, it even tells you at the bottom. It also suggests maybe creating a new branch at this point, but that's not what we're doing. That's not the workflow that we're in right now. What we'd like to do instead is to get the feature branch back to where it was. So we type git branch --force feature. Now, git branch is usually a command that you would use for creating branches. If you try to use it without the force flag on a branch that already exists, it'll say, no, I can't do that because the commit already exists. But all we're doing with the force flag is just picking that label up and plonking it on the commit that we've currently got checked out. So first head moved down to its current position and was detached. It wasn't attached to a branch. And we've typed git branch --force. And we've got the feature branch back down where it wants to be, but we're still in this detached head state. The git branch --force command has not reattached head, so we reattach it to the feature branch manually by typing git checkout feature. So we've gone from having both the head and the feature branch label on that blue commit at the top left there to having head actually attach a feature again. So now everything's exactly as it was before we did the merge, as far as we can tell. But if we add yet another flag to our log command, it turns out the commit wasn't actually deleted. The merge commit still exists. It's just not displayed under the log output unless we explicitly tell it to. The reason for this is that git log --all doesn't show you all the commits. It shows you all. Of course it doesn't. Why would it? It shows you all of the history of all of the branches. And that merge commit is not part of the history of a branch. It's not part of the ancestry of a commit which has a branch label on it, a branch pointer on it. So clearly it's been hidden because it was deemed not to be relevant. We've managed to convince Git to show us it anyway. And now we've concluded that it hasn't been deleted and that it's still possible to get it back if we reverse that position again on whether or not we should have done that merge. But what is the ref log? The ref log is a log of references, branches, times head has moved. It's a log of every commit that's happened, every time you've checked out another branch. We can see right down at the bottom that there's still a log of our merge commit being created. So if we wanted to get that back, if we wanted to redo the merge without having to address the merge conflicts again, if we wanted to have a new branch because we'd done the merge in the wrong branch, then we at least have the ID number of it. So we're able to navigate to it now. And the commit object is still there. As a matter of fact, as a sort of dead commit, as an orphaned commit, one that's not being used as part of the history of any commit with a branch pointer on it, that'll be cleaned up at some point. Now, depending on what Git version you're using, it could be a couple of weeks. There are times when it actually works by counting the number of reference changes. But it's still there. Now, we've talked about merge commits in the ref log. We've talked about branches and commits, obviously. I'd like to talk about rebasing now. Now, this is a subject that worries some people. I think it's fair to say that it is easier to explain what a merge commit is doing if you do not know very much about Git than it is to explain what rebasing is doing. There are lots of teams where rebasing is strongly discouraged. There are others where it's insisted upon. Moving from one to the other is a horrible experience, which I've had in the past. But the important thing to understand is that a lot of the myths about rebasing aren't necessarily true, and I'll make it clearer what I mean by that as we progress. This is what a commit graph looks like before rebasing. It looks familiar. Sort of the same repository. We've got a feature branch. We've got a master branch. There are changes in feature which are not in master. There are changes in master which are not in feature. We would like to update the feature branch to include what is in master, and ideally not doing a merge commit. So if we particularly want to have a clean tree-like commit graph, we can avoid using a merge commit for that if we want. How we can do that is by typing git rebase -- master. Now, it looks relatively simple what's happened here, but I'll talk you through it. The important thing to note is that the two grey commits at the top are the same colour. Other than the monochrome ones, the colour coding doesn't actually matter. But the two grey ones are the same colour. And why I've done that is to represent the fact that they're very, very similar commits. They have the same change set in them, unless there was a conflict. They have same timestamp, same author. Starting to make a little bit more sense now why we might talk about having an original commit, an original author and the person who created the commit as being two separate fields in the metadata, because the rebase wasn't necessarily done by the same user. And all that's happened here is that we've created a copy of some commits which were previously peculiar to the history of the feature branch. And we've taken the feature branch label, stuck it on the new copy, and head's been moved. Now, what Git's actually done here is it's effectively checked out the master branch and got head to the position that it's in the master branch. So it's got the local code to the point where it's got the code that's in master. And then what it's done is it's inspected the graph and to check how many commits there are that need to be copied. It's discovered that for simplicity I've only put one here, but this could have been several. And it's then played those commits over the top of the current position and then rechecked out the feature branch. Now, there is a popular misconception that the rebase command is somehow causing irretrievable data loss and destroying all of your work. That hasn't happened here, and I've done the git log command with the reflog flag just to demonstrate that the old commit is still there. So once again, what we've done is we've checked out master, created a copy, and then moved feature onto the copy. There's one other interesting thing to note about this new commit, and that is because it has a different parent than the one it's a copy of, it therefore has a slightly different metadata file. And therefore, when you hash that metadata file, you get a different ID number. So it's very similar, but there's no real sort of hard link between the two. There's no real way of telling beyond similarity of timestamps, commit messages, change sets. It's as if it were a completely new one, and the old one is still there. Now, what if we want to undo a rebase? Well, we've got an established procedure for this. We might incidentally have pushed the rebase already. It's still possible to undo it, but there'll be more on that when we discuss remotes later. And we'll have a look at the ref log now, and we can see where the old commit was. We can see that the rebase command has essentially checked out master while we're rebasing from master. And then it's played some new commits over the top with similarly with a familiar message but a different ID number. And then it's checked out the feature branch again when it's finished the rebase command. So by checking the ref log and finding the hash, we can now check out the old copy of the grey commit at the top on the left, and we can forcibly move the branch to that location, and we can reattach head to it. And it is effectively as if the rebase never happened. There's a dead commit lying around, but it's been simple enough to navigate to a different point in the commit graph, move the branch, reattach head, and we've essentially undone the rebase. So having spoken a bit about rebasing, just like to quickly cover cherry picking, which is kind of a similar concept in a way when you look at what it's actually doing, and then we'll move on to remotes. So we've discussed what a merge commit is, what it does, how to undo it in an emergency. Same story with rebasing. We've looked at the ref log. Now, a little while later, our repository is in this state. We've got two branches whose histories are disappearing off the bottom of the screen, because it's a very old repository now and it's got lots of stuff in it. And in this contingency, we want to get that black commit that's in the middle on the right, and we want to get the code that's in that commit into the feature branch. So imagine, for example, that we don't want the whole of feature 2 in feature, we just want a particular commit that does some individually useful thing. We want that in our branch. What we really want to do is to be able to copy the black commit. So we type git cherry pick and a hash, and it does exactly that. So it's taken a copy of the commit. It's got the same change set, probably, unless we had to resolve a conflict. It's got same timestamps, original authors, same commit message. The only thing that's changed is it's in a different place on the graph. This obviously means, again, because of the way Git's producing these ID numbers of these hashes, it is actually a different commit because the parent ID is different, therefore the checksum's different. So in this example, for the sake of simplicity, I've only cherry-picked one commit. You can actually put as many hashes as you like and it will cherry-pick them all in order for you. But in this case, all we've done is copied one commit to another place in the graph. Now, I'd like to move on to talking a little bit about working with remotes. We've covered a lot of local operations now. I'm going to talk about remotes and pushing and pulling. So the first thing we're going to need to do is to create a remote. In this case, I've created an empty GitHub repo, and I've typed git remote add origin, and its URL that you could have used to clone it if there were anything there. Now, there's nothing special about the word origin. It's conventional if you're only using one remote for it to be called origin. If you clone a repository without telling it what to call the remote, it will call it origin. but it doesn't have any sort of special status. You can have several. This is useful, for example, if you want to have a different backup of your repositories locally in your office for GitHubs down, whatever. And we've typed git push set upstream origin feature. Set upstream is now optional as of Git 1.7, Lorna? 1.8, thank you. So the set upstream is asserting that we're creating a new branch on the remote. If the branch on the remote already exists and we say set upstream, it will tell us that it's not able to do that. But if we'd omitted this flag and it had never heard of the feature branch before, it would have just created it for us in more recent versions of Git. And it tells us on the last line of output that it's created a new branch. Now this is our diagram, and this is getting even more exciting than previous diagrams because there's 2 columns. We've got, on the left-hand side, our local repository that lives on our computer in our .git directory, and another repository that's very, very similar in the way that it's stored on a remote. And having pushed the feature branch to an empty repository, Git's copied its entire commit history for us. Nothing else, nothing that's not part of the ancestry of this commit, which has the feature label on it. And that's now sitting there ready for other people to push to or for other people to use. The necessary commits have been sent over the wire, but none others. The master branch wasn't sent. And one other interesting thing's happened. Another branch has turned up in our own repository called origin/feature. This is a tracking branch. Tracking branches are very similar to normal branches. It's just a pointer to a commit. You can't actually check them out and commit to them. That doesn't mean anything. It's just a record of this is where the feature branch was on origin the last time I talked to origin. That's what that means. The last time there's any communication on the network about this branch, that's where it was. So we've had a look at our local repository. We've noticed that there's now origin/feature and feature. They're in the same place. As far as we know, they now contain the same things, not necessarily going to stay that way forever. If we now type git push origin master, the master commit gets copied. Now, what's actually happened here is not that Git has sent the master commit and its parent and its other parent over the wire. It's simply identified, it's talked to the remote, it said, do you have this commit? Remote said no, but I've got, do you have this next commit, which is its parent? Yep, got that one. Okay, so I only need to send one commit to you. And so it's transmitted this one other commit, and we've created another tracking branch, another fun sticker for our whiteboard, to represent where the master branch was on origin the last time we checked. Sometime later, it's possible that information can become out of date. In this example, somebody else has put some code in the master branch which doesn't exist locally. Now, if we type git fetch, it'll simply copy that commit back and update the tracking branch. It's not going to change where our branch is, but we can type git fetch to get information about the branch and where it is on the remote. We may want to update the master branch, we may not, but at least now we have all of the commits that are relevant to it. And the tracking branch is in a place that reflects what was going on the remote the last time we checked. If we want to update that master branch, we can use git pull. Git pull by default does a fetch and a merge, which means essentially fetch, move the master branch to the latest position, and move the master tracking branch, origin/master, to the latest position, and then do a merge. In this case, merging between the commit that's on master and the commit that's called origin/master, the git merge command itself will decide it doesn't need a new merge commit to do that. It will just pick the label up and plonk it. Because the two aren't divergent. One's part of the history of the other. But so if we just type git pull, then master will be updated. Fast forward only pulls are another kind of pull you can do, which absolutely ban creating a new commit and say, I only want to update by fast forwarding, and if you can't update by fast forwarding, then stop. So if, for example, we were to try to do git pull -ff -only to pull the master branch into the feature branch, it will say, no, I would need a merge commit to do that, so I'm not going to do it. And the other kind of pull is a rebase pull, which essentially means do a fetch and then rebase on top of where the tracking branch is. So if we check out master in our example and type git pull -ff -only origin master, it'll do a fast forward to update master. In fact, because of the way the merge command works, it would actually have done the same thing if we'd have done this same command without the fast forward flag. To give an example of a pull creating a merge commit, I've checked out the feature branch and then pulled origin master. Now what this is involved is automatically creating a merge commit that's merging what's in the feature branch locally with essentially what's in the tracking branch, what's in origin/master. So we've updated origin/master to the relevant position, and then we've created a merge commit. And there's one other way we could have achieved a similar effect: git pull --rebase origin master. That's quite a common command to use if you're using a workflow where merge commits are discouraged, where the repository is supposed to be tree-like in structure. You want to update from a default branch quite regularly. Git pull --rebase. And what that's achieved is we've now created another copy of the commit that we had locally that was in feature. And we've moved the head and the feature label to it. If we now try to push feature, it actually rejects it. It says, no, you can't do that. And the reason for that is that it would amount to removing a commit from the history. So we've created a new copy of the same commit, which we're trying to push, but we're also kind of removing the thing that it's a copy of from the history. And Git said, no, that would involve deleting something, so by default, I'm not going to do it. If, however, we type git push --force, then it will forcibly move. As a matter of fact, if we ignore the slide completely and type git push --force origin feature, then it will push the feature branch. So what we've essentially achieved now is the lower monochrome grey commit has been removed from the history of the feature branch on the remote, and the new one has been added in a new location in its place. On the diagram I've represented the old grey commit on the remote, that one. Oops. What in the world's happened then? This is all part of the plan, I assure you. On the diagram, we've represented the old grey commit as still existing on the remote. That actually depends very much on the settings. They do tend to disappear. For example, on GitHub, they do quite aggressive garbage collection settings to get rid of things that aren't being used anymore. But if we decided that we didn't want to, or that we regret having force pushed this branch, what we can do to solve that problem, remember, is we can always check out the old copy of the grey commit on the bottom left. We can always check that out and force push that if we want to. So we can check it out by its hash, having found it. If we want to undo our rebase and force push, we can relocate the local branch there, and then we can force push the position of the branch. So we've undone our rebasing and force pushing that we previously used to update the feature branch because we decided we didn't like that. So git push sends changes to a remote. If the remote branch has commits that aren't in the local branch, it will fail. Force works if the branch has been rebased. Force with release is a much better idea. Force with release, the only difference is it's checking if the tracking branch is in the correct place first. So in this previous workflow, somebody else could have been committing things to the feature branch that you didn't know about, and your force push is essentially removing that information from the history when you didn't even know it was there. So if you use force with release push, it will check that the tracking branch is in the right place. Does this user actually know what they're force pushing over the top of before I agree to do it? So we've talked about commit storage, branch storage, merge commits, ref logs, rebasing, cherry picking, and working with remotes. I think we've got time for just maybe one question, or possibly two. Any quick questions anybody would like to ask?
Is it rude if I ask a question? Oh, here we go. People volunteered to save themselves.
Is there any difference between git pull rebase and git rebase?
Well, it's fundamentally what it's doing is it's doing a fetch and then doing a normal git rebase command. So you can do that manually. You can fetch and then rebase on top of the tracking branch if you want to. It is the same rebase code. It's just git pull -- rebase is actually doing a fetch and pulling down local code from the other repository as a first step to doing the rebasing. Does that answer your question? Thank you.
Cool. Anyone else? Got a couple of minutes? Yeah.
So what's your opinion on using rebase and merge?
What's my opinion? I promised in the talk abstract that I wouldn't proselytise and I wouldn't tell you all what to do and tell you which workflow is right and which is wrong.
Well, that's why I asked your opinion on it.
If we all work hard, then together we can stamp out merge commits in our lifetime.
I like it.
Thank you.
Awesome. Okay, so we're going to wrap that up there. Thank you so much, Sam.
Thank
This was
you.
awesome.